Okay, so based on what is your TA is also giving me, uh, so I will maybe take some time to review uh, last Tuesday. Okay, can you hear me now? Okay, now can hear it. Okay, okay. Oh, okay. Okay, now I know the problem. Okay, now you derive the equations, uh, plug in the x or the point that you want to observe, evaluate. You get the slope, put the slope into the line equation, and that is your tangent line. And I think, yeah, okay. And this is the little board. And for the second questions, I'm really sorry. There is some mistake in the system, so I couldn't get your answers. I get the first time, but then I'm not sure how. But the system is technically have a problem, and I think the time is not enough. So I'm sorry. It's too short. So maybe next time I will keep the time. Maybe can be around 2 minutes. Okay. All right. So how to solve this? This is basically the chain rule. Okay. So let me write here. This is r of x f. Okay. If the composite only having f and g, that's pretty much easy. Let me write here first. If this rx is just having f and then g, and then we want to take this derivative, we can do just usual chain rule. So this is our solutions, right? Right. But if you have more than like for example, you have like a sandwich, so inside the function, inside the function, inside the function, as many as you can hear, it's actually similar idea, but you need to be more, you need to be careful. Okay, so first, let me write. First, you have the f prime, okay, at the beginning. So if you want to be more careful, you can write slowly, and then you can write here is pdx of g h. Write slowly, and then you will slowly fill in all the lines. Okay, so you start with the f prime, and then you need to derive the inside. Okay? You need to derive the inside. So again, this is outside, right? Outside function. This is inside. But the inside functions, it has another composite. So you need to derive this. And how to derive it is precisely what we have done, like in the usual chain rule. So we can derive this, write this as g prime, and then write the inside, and then multiply with, because I think the last term is the h, so we can just take h prime there. So we can write completely. Okay, we have all this three components here, and this is our final derivative. And the rest is we plug in the x equal, I think 1, right? We plug in 1, and then check within the information based on the question. Okay. So this will be r prime x, right? And then we plug in 1. So we plug in 1, 1, 1, and 1, right? And look at what we have. Let's see. H1 is 2. Okay. H prime 1 is 4. I think that's enough. So H1, this will be 2. H prime 1 is 4. H1 is 2, so this is whole 2. G2 is 3, so the whole is 3. F prime 3 is 6. F prime 3 is 6. And G prime 2 is 5. This is 5. So 6, 5, 4. So this will be 6 times 5 times 4. This will be 120. Okay. So for me personally, if I get similar question like this, I would like just to make my line first. What's the final derivative, and later put in the number, and then get the result. Okay. Because if you put the number first here, maybe you will mix up between the derivative and not the non-derivative, right? So I will make this first, and then later just plug in and then solve one by one. So it's like preparing, maybe if you like to cook, it's like preparing your ingredients one by one, check one by one, and is it correct? Is it correct? Is it correct? And then finally you get, oh, I get all the results. If you are maybe you have confidence and then you already know how to solve, you can directly go here without these steps. But if you want to be more careful, you can write this step here so that you can avoid mistake. Avoid mistake. Okay. Okay. By the way, because of the system error, I cannot get your answer here. I cannot download the results here. So I would like to ask which one is Curry? Is it in the classroom or no? Okay. Is there anyone who named Curry last Tuesday? Can I have your your ID? Student ID you can write. Okay. Okay, and then some suggestions. Okay, about the quiz, the timer especially. Okay, so I think I can make some additional time for you. Okay, and more practice with the answers. I will provide that. I think this week. Okay, it's difficult. Of course, it will be difficult. Every student who learn calculus, and yeah, most of the students will think that it is difficult because it is, because it's very basic, and most of science and engineering will base on calculus. So if you not really doing well in calculus, you will have difficult time to move forward. So that's why it's difficult, and it's already have been so long. Like the one who invented calculus is Newton, which is a long time ago, right? And then oh, someone asking more questions on quiz. I will think about that. But that's okay. Okay. Difficult. Okay. I hope teacher can stop. Okay, maybe I will stop for you to taking some notes. Okay. Okay, I think any question from here, from the general here? Okay. So the key for any derivative is, if you are not confident, take slowly. Take slowly. Okay. Yeah, take slowly. I think that should be a good advice for you. Okay, let's continue a little bit. Because last time there are, I think, a few students asking about the implicit differentiations. Let's go back a while and take a look uh, the idea of implicit differentiation. Let me draw first some. Let's say this. Okay. So let's say this is um, a ladder. Let me write a ladder, and let's say this has some length here. I just make it beautiful in triangle. If this is 5, I think it can be 3 and 4, right? But then the question is, uh, if the ladder, let's say this y direction here, so the ladder is going down. So imagine, let me draw uh, what would it be when it's going down. So the green one is how the ladder moves. Okay. So the information we got is the ladder moves with velocity in this direction here, or maybe let me, this is 1 meter per second, and all is in meter. Okay, all in meter. 5 meter, 4 meter, 3 meter. And the question is asked, what is this velocity here? Okay. I hope from this example you get the idea why uh, implicit differentiation is important. Okay. So this problem is uh, I I take from 3.9. It's about the related rates, but I think it also can be useful in implicit differentiation. Okay, so first, what will happen if I'm putting here the ladder is going down, 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 down? Of course, this length here will be reduced, right? The one that are touching the ladder, the length in this area here. So the length here will be going down, right? Reduced. So this is 3 meter. So maybe it's going down, going down. And the length in the 4 meter here will be increasing, right? The one that is touching the ground. Okay. So first, to solve this, we can make name. So take name. Let's say this is y. This is x. Okay. Just naming. Okay. 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 Now to connect all names here, so to relate all the terms, all the let's say all the terms in the problem, we need to come out with I think with a formula that connects all the things here. So if we have x and y, and x and y can be changed according to the ladder, right? So x and y is a variable. You have two variables. because when y is changing, x also change, right? So let's have a formula. But because it's a triangle, I think the best formula that we can approach to connect all of that is just x squared, right? Let me write x squared plus y squared equal 5 squared. I think this will be best way to approach and connect all the formula, right? Okay. Now, the idea here is if we take, because all is in meters, right? You have another actually variable, which is time, because you are talking about the velocity, right? The direction going down, and then it's asking how many are going left, how fast the ladder is going to the x left directions, right? So the idea is if y is reduced, then x is going to be increased. So let's say we have so because it's a rate of change, right? Let's say rate of change with respect to some t, right? So we can also say we can take derivative with t. So we are introducing the new variable t to make up all the requirement here. So we take derivative, we take 2x, and then we need to take another, because it's respect to t, we take the dx and dt. Okay, so let me write here and then let me make another example later. And then plus we take y, and we also take the derivative. Okay, and this equal 0. Okay, now if you look here, dx dt is going to the left, and it makes the length increasing, right? It makes the length increasing. But here the length is decreasing, right? The length is decreasing. So you can take this 2x. This is the dt, the one that we are talking here. This is the x dt, and plus 2y, and then this will be dy dt. We know the dy dt is here. It's 1 meter per second, but it's decreasing, right? In case of decreasing, I will take this as my -1 here. And x and y will be a fixed constant. 2, 4, this is 8 dx dt. That is 6, but -6. So dx dt is 6/8, or 3/4. Okay. But actually, the sign here, if you see this negative sign or positive, it depends on you. Depends on you. If you say going to the left is negative, then that's still okay, as long as the definition are correct according to the information. So you can say, because I make 3/4 positive, and I make the definition that positive means that the ladder at x-axis is increasing. So I can say that dx dt is equal 3/4 meter per second and it's going to the left. Okay. Okay. Now from here, okay, from here, what I want to show you is that x and y, okay, x and y is independent. They are not really related, right? Okay. Okay. Now, okay, let me give you time to write this and think, because this is actually still a few sections up from what we have now. Okay, but I will give you today because I think it's related to the implicit differentiation. Okay. Okay, from the ladder, we know that when you are changing your y, you also changing your x. Okay. Now let's see. I hope you guys finished the notes. Okay, uh, let me add, and let's make a circle, and let's make the same. Uh, let's say this is 4. This will be 3. Then this will be 5. Okay. Now this is the problem that we are dealing with the implicit differentiation at the beginning, right? And let's say we have, let's say uh, we want to know this tangent line here. Okay. Now imagine I will make some movement, and then okay, let's say we have another line here. This is also 5, right? This is also 5. And then I have another tangent line here. Okay. Now imagine your line or your radius here is rotating, going through. Okay. What's happened with the line or the point here? Okay. What color I'm using now? Okay, so you have, let's say that, and that is here. Okay, let's say we have, this is, like, this is dy, this is dx. So when you move, you will see that this dx and dy, they are changing. But the ratio of that change is the same. Right? Okay? It's the same because they will always make the line is the same radius. Okay, so when they are moving to here, so maybe when they are moving to wait. So when they are moving here, dy and dx, they are interchangeably changing. So probably when dy is getting larger, maybe dx is getting decreasing. When dy is getting decreasing, dx may be getting larger. So that the x squared and y squared is always 5. Okay. And now from these equations, okay, from these equations, of course, this is y is actually not really related to f of x, right? But we can make that happen if we are going to take some time to simplify this and then we can make something like this. We can have the positive and negative. We can make some relation and we can make that this is okay. We can make this is actually maybe true. Okay, that this is a function of x. Okay, but actually because this is y and x are independent, like we have seen in the previous ladder, the ladder part, then we need to take some tools. We need to take some tools to check, right? We need sometimes to check, can we differentiate this, right? Can we differentiate this? That's why, okay, the system of this derivative is called implicit, because we implicitly make y is actually a function of x. But that is actually not quite correct. If you see the circle, it's not quite correct. But we make it like y is f of x. Okay. That's why the beginning for the implicit is actually we take each variable with each dx and dy. So for example, this is derivative. We take derivative here. We take 2x dx plus 2y dy and then equals 0. And then you can take this and make it, oh, okay, we can make it dy dx. And we can make that, okay, then we can make that y is a function of x. But because y is inside the functions, when we take derivative of y, we need to take this dy dx inside. Okay, so whenever you find x squared plus 2xy plus 3y squared equals 0, when you differentiate this with respect to x directly, then you can directly do x, that's okay, and then plus. Now this is having product rule, so 2, let me write the bracket to take some time for product rule here. So x, y, so y plus, okay, x, and then dy dx, and then plus 6y dy dx equals 0. And now the derivative you are looking for is inside the equation. Then you need to solve the equations. 2x plus 2y plus 2x plus 6y dy dx equals 0. 2x dy dx. So dy dx is 2x plus 6y negative 2x negative 2y. Then you can solve this. At least we have this expression, okay? So now because we have these tools called the implicit differentiation, then whenever you see any y inside the equation, we can take the derivative with respect to x, okay, with respect to x, and treat y like x, but we need to add this dy dx because we make as if this y is function of x. Okay, okay. So that's why the name is implicit, because we make like that the y is actually function of x, which is not quite true, but we make it somehow into our equation. Okay. Okay. I hope you understand that there is an implicit, explicit. Explicit is something that is obvious, right? Implicit is something that are inside, but it's not quite obvious. Okay. Okay. And this is actually uh, just the beginning for we call multivariable calculus. So this semester, your class now, until our final exam, we will learn. It's called the single variable calculus. Single variable calculus. The next part of calculus, which is calculus 2, the next semester calculus, that will be multivariable. So which means our ideas today in our class still using single variable, which is x. Although we have this y, we still have dy dx, right? The next part on your calculus, we will differentiate each of each variable. There will be another method. Okay. Okay. So maybe uh, let me write here to take some notes for you. So this is single variable calculus. So this is um, semester, the first semester, semester 1, okay, and then multivariable calculus. This is semester 2, second semester. Okay, and implicit differentiation has, I think, some benefits. Okay, some benefits to solve some equations in terms of x. Okay, in terms of x. Okay, I hope you already guys have see the page here. Okay, okay, let me go on. Okay, let me move to. I think I'm I'm giving you the questions about this. Okay, so one way to solve this is actually using the implicit differentiation. Okay, okay. First, let's just say we want to make this squared. Okay, both sides squared. Okay, both sides squared. We get y squared and then x plus this whole thing here, x plus right? Okay. And in math, if you see this terms here going infinity, right? The question is square root of x plus square root of x plus square root of x, and then it's going to have plus plus plus, going to have more and more unbounded. If you square this, get x plus, same thing here. It's unbounded also. Okay. So I can write this as y squared x plus y, right? Right? Correct? Okay. Because it's the same property, it's going to have infinite and unbounded. The next thing, move a little bit right. Next thing is I take the derivative, both sides. So I will going to use the implicit differentiation. Of course, you get the idea that this will become 2y dy dx, right? 1 plus dy dx. And then we can write this dy dx 2y minus 1, okay, equal 1. And we get dy dx is equal 1 over 2y minus 1. But it still has y. So in implicit differentiation, we are going to take y and changing into x. If we have the equation, we need to take all y and then change into x. So this will be, the result will be 2. Y is, we take back our original equation, minus 1. And this will be the result. So implicit differentiation has some benefits, especially if you have two variables in one equation. So you can take implicitly as the two variables related to each other. Okay, so you take the dy dx. Okay, hope you guys get my point here. Okay. This is one example how we can use implicit differentiation to solve some maybe a complicated problem. Okay, next thing here is, I think we left, the last thing we discussed is we have this as in our definition. Okay. So this is about the log, the ln. And we prove it last time using the implicit differentiation. from this b with power of y is equal x. We take differentiate both sides. This will become b, y, ln b, and then dy dx. And this will be 1. So dy dx is equal 1 over b, y, ln b. This is 1 over x ln b. And if b is e, then ln e is 1. And we can take this into our formula for the ln, the natural logarithm. Oh, by the way, I'm just uploading the video about the exponential and e. I hope that can help you to elaborate more. And I think I have one recommendation for you. There is one YouTube channel that has, I think, good visuals to look at how the implicit differentiation looks like in the real world, and how how can we get the e, and what is e used for. Yeah, I think I will also share it later. Okay. If we have y equal ln x cubed plus 1, what is y prime? This is based on the derivative of ln x is 1 over x. So if you have ln and then x cubed plus 1, can you derive this? Let me give you some time to check. Okay. Okay, one way to solve here this differentiation is, let's take some another variable, let's say u, and let's probably this is the x cubed plus 1. Okay. If I'm only having the ln u, then y is ln u. So we can look at the ln u, we have the dx, and then, or we can also say in this ln gx. So we have dy dx is equal dy du multiplied with dy dx. Or in this case, dy du is 1 over u. 1 over x cubed plus 1, and then du dx is 3x squared. Or if it is simple enough, we can directly uh, directly look at this ln here. Look at this ln, and then if you differentiate, the whole thing here becomes 1 over x cubed plus 1. Multiply with the chain rule. The inside function is x cubed plus 1. Differentiate 3x squared. So 1 over x cubed plus 1 multiply with 3x squared. Or if you want to be more careful, you can take some u to make it into x cubed plus 1. Take this, and you have this dy du du dx. Okay, you can take this also if you want to be more careful. But I think it's simple enough for you to just directly get the answers. Okay, this is just to show you. You can also rewrite the inside function as any variable you want, t, u, v, okay, to help you to get the solution. Okay, I think too small. I think here. Okay. Okay, let me give you this question. Okay, this is the questions. So the question is, find the first derivative or dy dx of the equation is y equal ln x plus 1 over square root x minus 2. Okay, let me give you some time to think and check. Okay, for online students, Do you have any idea how to solve this? You can write your method, what you can do first before you solve it. Do you have any idea? Okay. Now, uh, in calculus, uh, the calculus problem is just finding the first derivative, right? But how to find the first derivative, we can approach with several methods. But I think the best way to solve this is by looking at the ln this ln. Okay. If you remember, you have any log, or let's say ln, we can write this as, right? Do you think it will be solved better? It can solve at least two ways. The first way is doing the uh, 1 over x plus 1, and then d dx of this x plus 1, which is still, I think, still doable if you would like to take this route. But this is, I think, you will have this f over g. You need to do some quotient rule and take some time to derive f g, right? Let's see here. Okay, let's take this y is equal ln this x plus 1 minus ln. Okay, and then let's take the derivative. Let's take the dx. This will be 1 over x plus 1 minus, it will be 1 over 2, 1 over 2 squared, 1 over 2, 1 over 2, and then squared x minus 2 multiplied with squared x minus 2. It just take the 1 over x minus 2, and that's finished. So another way to think is, if you have any ln, then any rules that has in the logarithm part, like a over b, or another way is also, if you have this ln and a multiplied with b, you can take this as ln a plus ln b. Okay, and sometimes it's better to separate. Okay? It's better to separate. So now at least you have, uh, for me, the derivatives that are really powerful is this ln and the implicit differentiation, because with these two, we can prove most of all formula in derivatives. I will show you later. But at least this case here, the question here, you can always relate to the law in logarithm, the law in logarithmic. Okay. Okay. All right. Okay. And let me like zoom out here so you can have maybe more. Okay, let's continue. I will have some notes for you. It's about the ln. So we already discussed that if you have ln x, you can differentiate it is 1 over x. But if we have this, if f of x is ln, but with absolute value, so we need to also think that we may have two different answers because we have when x is at least greater than 0, x positive and x negative, right? So we can have this piecewise definition for the ln absolute value x. The first one is ln x. The second one is ln negative x. And this is important to keep in mind because later in I think in the chapter 4 or 5 about integrations, this definition will be important. So this will be if x is greater than 0. This is if x is less 0. Because the derivative of this ln absolute value also different. But then this is 1 over x. Do you agree? Do you agree? So here, let me write here. ddx of ln minus x. Okay. This will be minus 1 over x. Multiply with ddx of the negative x, right? So that's why it's become the same 1 over x. See, it's ln x, ln negative x. If you draw the graph, it's different, right? If you draw the graph, this will be ln x, this will be ln negative x. Okay? So this will be ln x, this will be ln negative x. The derivative is just 1 over x. Both cases, 1 over x. So later, let me just make some notes here, but this is not really in this chapter. So if you have integral of 1 over x dx, it can be ln x, or it can be ln negative x. So it's better to write ln absolute value x. But this is just to keep in mind, okay? Not really in this chapter, but later you will see that when you are take the antiderivative, you take the integrations from the 1 over x, it can be ln negative x or ln x, okay? So this is, I think, important to keep in mind. Okay, now, like I said before, We have implicit differentiation. We have the log, the ln. Now let me give you some idea here. We now have we know that if we have this, then our y prime is n x n minus 1, right? That's from our basic concept. Now, if we are going to prove with the implicit differentiation, we can also prove this. So we are going to take ln also here. And then we take the implicit differentiation. This will be 1 over y dy dx equal, let me make it a little bit bigger. This will be n and then 1 over x. This will be n, 1 over x, and then y. Y is x with power of n. So we can also prove the power rule with the implicit differentiations. So anytime you have maybe some, you think that maybe the equation is really maybe a little bit complicated, sometimes you can take this idea, take the ln both sides, especially if you have something power here to take it down. Maybe you can imagine the n can be maybe another function, maybe x squared plus 2x, and it seems, oh, how to solve it. You can take ln and make it down. Like for example, okay, if you have ln maybe x plus 1, like that. If you're having just this, okay, just this without any ln, then you can let this whole function here be a y. Okay, let just this be a y. Take ln both sides, and then you can solve using implicit. Okay, and I think most of the derivative can be solved this way. Okay, any questions? Okay, any questions from online students and also from this classroom? If there are any questions, I will take some time to. This is the power rule we already know. We can prove also with the implicit. I will go through one by one the product rule, quotient rule, and see can we do some implicit and do some proving. Because if you can do well in implicit, if you maybe forget what you have learned, like in product rule, quotient rule, at least you still remember the implicit. You can prove all the rules using implicit. Okay. I hope the notes is okay. So this is proving power rule using implicit. All right. Okay. Okay, let's take another page. Hope you finish this. Okay. I will go back later if you would like to review. Let's say product rule. Product rule, let's say we have um, let's use y because we are going to use the implicit so that you can relate to dy dx. Okay. Both f and g are continuous function. So first, you can take ln both sides. And take the derivative implicit, so this will be 1 over y divided dx. And this will be 1 over f. And then let's say it has the chain rule, so you need to multiply with the f prime. It also has the chain rule for g. It takes some time there. So dy dx is y is fg, so I will write fg. And this solving this, making fg f prime g plus g prime f. And cancel this, and you get your product rule. Okay. I hope you can try the same as well with the quotient rule. I think you can do by yourself. And I would like to show you another way to see the e, okay, another e in this case. Okay, let me take some notes. Okay, so you know that from the ln. So if you have a function of ln, you have the derivative is 1 over x, right? And then if you plug in 1, then you will also get the results 1. So from the definition of derivative in limit, we can take the derivative as limit h approaching 0. And this will be, let's take the x and change all h with x. This is the same thing, just changing the h with x. And then take the ln. So fx is ln x. But change all with ln 1 plus x. This is minus ln 1 over the x, and then limit as x approaching 0. We can write 1 over x in the front, and then we can take ln 1 plus x, because ln 1 is 0. Right? Now we have these expressions. Limit as x approaching 0 is ln 1 plus x, and then we are going to put 1 over x and put into the power of 1 plus x. Okay. Because that is the ln law, the log law. And we know that the f prime 1 is 1, right? So the whole thing here is equal 1. Okay. Okay. From here, okay. So we have this. Let me make some box here. Okay. 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 From exponent, we are going to see that e. If we put 1 here, it's still e. Okay. And then we can also exchange this into our limit. And this will result in the limit. We can write this in terms of e ln. Okay. So whenever you have e and it have power limit, you can take the limit factor outside. Same thing. And this will be limit as x approaching 0 of this cancel. And we now have e is equal this. And then how we can make sure that this is true, you can try to draw the graph. I forgot to make the graph here. So let me just draw some illustration for you. This is 1, 2, 3. This is 2. So probably around here. Yeah, more or less this is it. This is y equal 1 plus x with power of 1 over x. Okay, n if n is our 1 over x, okay. So as x is going to have approaching 0, then n will approach infinity, right? So we can also change this expressions with e equal limit as n approaching infinity. This will be 1 plus 1 over n. I think there's another way to take this e. We can prove this from a compound and interest formula, but I think we don't have time today. Maybe later I will show you. And we know that from here, from the graph itself, from this function here, this is e. We get 2.7182818, blah blah blah. So another way to get e. Or you can take also approach from x, maybe a lot of 0 here. Take to your calculator, you will get the e. You will get the e. But then we have okay. Because we only have maybe around 10 minutes left. There is one section, this about the inverse trigonometric, but I think I will let that inverse on next week. So now I will have more exercise so you can have more practice. Okay, any questions from online students or also from the classroom? Okay, maybe I will give you some practice for today, and you can let yourself to try and solve some problem. Okay, let's try some exercise for you. I hope the note is okay. Okay, exercise. Find dy over dx. First is, so I took it from, I think, previous question in, I'm not sure it's quiz or midterm, but I think it's from last year and last 2 years. Mm, let's say this is part A, this is part B. Okay, so you at least have 3 questions. The first part A, find dy dx. First one is square root of x plus square root of y equal 1. Second one is y equal x with the power of 1 over x. And the second part B, another whole question. You have A and B is continuous. Uh, wait. This means A and B is a constant and y is continuous. Sorry, is constants and y is continuous function. Sorry. And you have the function equation y equal a sine x plus b cosine x, and it is satisfy the equation. It's actually differential equation y double prime plus y prime minus 2y equals sine x. The question is find the value of a and b. Yeah, write the question first. Maybe I can just solve maybe 1 or 2 questions. From this question, which one you want me to solve? from this tree? The first one, the second, or third, or the last? Which one you want me to solve? Which one? Because I think we don't have time to solve all three. So yeah, the third one. Okay. Yeah, I think the first one and the second one using the ln, using the implicit. I think you can finish all the results. So take ln here, ln going down, differentiate product rule. Okay, and take slowly. Okay, take slowly, take slowly. And I think the more you are doing this ln and then doing the implicit, you'll be an expert in in technical differentiations. Okay. Okay. Now the last one, the number B, is basically you need to first look at the questions. This is y, right? It has a sine x, b cosine x, and this is the equations you are observe. So you need to have y double prime and y prime. So first, try to look for y prime. So y prime is a cosine x plus or minus b sine x, right? You derive once, okay, and then derive one more time to get the y double prime. You get negative a sine x, negative b cosine x. Okay, and then you get y double prime plus y prime minus 2y equals sine x. Writing y double prime minus a sine x minus b cos x plus and minus 2. The equation itself is a sine x plus b. Oh, I'm writing too large. Let me resize. Like here, b cos x, this equals sine x. Okay. So the idea is grouping sine x and cos x. So you will have sine x, blah, 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 a and b, right? You will have something like that, and then maybe plus or minus cos x, and then you have a, also b here, and it should be equal sine x. So what you can have here as your result is, I will not write all, but I think you can do it after you're in these rules. So sine x will equal with the sine x here, right? So everything inside here will be equal 1. That's first equation. Cos x. Everything here, a plus something b, something a, something b here, equal 0. You have two equations. You can get your a and b. Get it? Get it? Okay, I hope you get it. Okay. You can try solve this, grouping sine x, cos x, and then solve a and b. Okay. Okay, I hope you get it. The answer should be a is negative 3 over 10, b is negative 1 over 10. You can try by yourself, and then if you get the result, the answer should be a negative 3 over 10, b is negative 1 over 10. Okay. Maybe I will show you the rest of it, upload maybe later, but because now we don't have really much time left. So any questions first? Online students, do you have any questions? You can try also for the questions, all the questions. Okay. Okay, if not, then we will have our feedback today, and I'm already adding the timer so that you can have more time to think and calculate. Okay, I think we can start to working on. So this will be representing. This will be yeah, the title has an inverse, but you can ignore the title. Okay, have you scanned? Join the QR code, or just go to the menti.com and use the code 76051349. Oh, by the way, next Tuesday we will be in online class. Okay, because I will have a vaccination. Okay, in the classroom, have you finished the scan? Okay, maybe we can start. We can start. All right. Okay. Okay. Let's start for the first question. Yeah, 2 minutes. I hope enough. Okay. If you get the results, you can choose the correct answer. You have around 25, 24. Okay. 20 seconds. 3, 2, 1. Okay. All right. Okay. Most of you get correct answer. Okay. Okay. Let's see the next one. Okay. Jensen is here, Eve, right? Jensen? Right. Okay. Okay. Next question. Okay. Get ready. 3, 2, 1. Yeah. This is just see the is it true or false. So ddx ln 10, and then it's 1/10. Yeah, it's too small here. So I think if you are using your phone, I think it would be bigger. Yeah, the time is short. I'm just giving 30 seconds. Yeah, true or false? Yeah, just choose which one. Okay, it's ln 10. It's a constant, right? Okay, so it should be 0, not 1/10. Okay, next question. Okay, all right. Okay, magical rhino. Okay. Okay, question 3. Yeah, you need to see the phone. I think I'm giving you, I think, 1.5 minutes. You need to find C and then write the number C in your answer. The number only. The number. Only the number. Is it 0, 1, 2, or any number you find? I hope the time is enough. I hope. Okay, some students get the answer. Yeah, 43, 42. I think the time is too short or enough. Okay, around 20 seconds. Okay, hopefully you get this correct. Okay, time's up. Okay, not bad. It's 7. Yeah, I think some of you get the correct answer. And then who will be the first one? Oh, still Magical Rhino. Still Magical Rhino. Please write. Who's Magical Rhino is here? No. Can you please write your write your student ID? Okay, I think that's it for today. So thank you. And is the last one too short? The time too short, or it's okay? It's okay, right? It's okay. Okay. So for calculation, I think 1 minute to 2 minutes. I think that will be okay. Like for short calculation. Okay, right. Yeah, the class is over, so you can leave the Google Meet link and see you on Tuesday. And probably I will announce the result for your quiz maybe this week. maybe tomorrow, maybe Friday. I think some of you not using your real name, so I'm quite confused. So I will post some announcement on the Moodle and maybe the Google Classroom, because I don't know whether it's that the students in our class or no.